Hi, so we're going to talk about recurrent neural nets, and this is going to complete our discussion about artificial neural nets and complete the course in general. So recurrent neural nets are designed to use temporal dynamics to model temporal dynamics. The basic idea is that if you have inputs that come as a time series, and maybe it's a time series of something complicated like images, then you can have your x1 is your first time, t equals 1, x2 is t equals 2, x3. These are different input variables, which we could just take them to be elements of RP. And then what we're going to do is we're going to start to build a neural net from these inputs by creating some sort of a hidden unit, which also appears as a is sort of temporally ordered. So this x1, function of this x1 is going to be a hidden unit h1. So just think of it as a single random vector. Presumably it's of smaller dimension than x. And then the next hidden unit, h2, is going to be a function of both x1 and h1, right? And h3 is going to be a function of x3 and h2. And so all of the previous time point inputs are going to be expressed through the hidden state variable. So this is the hidden state. This is the hidden state. We'll just call it units, because it's not a variable because we're not giving it a probability distribution. It's a unit. It's a function of the input vectors, where the x sub t is the input at time t. Okay, so how does this differ from the IID setting? So thus far throughout the course we've been working in the IID setting for the most part. And in the IID setting, the basic idea is that each time, or each xi, is independent of one another. And so there's no distinction between h1 and h2 in those cases. They're not connected to one another. They're just functions of their inputs in that case. Right? So if like x sub I was the ith input, if we assumed independence, then there should be no connection between h1 and h2 in that case. But in this case, we're not going to assume independence. They're just different inputs. Okay. So for example, and this of course is our computation graph. What I'm drawing here is our computation graph. Okay. So let's think of an example, because this isn't very clear until we start thinking of specific cases. So this is common, is just to let xt be 0, 1 to the p, and is a one-hot encoding of a word in a dictionary. A word in a dictionary. And this is a there are p words in total in the dictionary. So this is an extremely high-dimensional vector. Right? So you can think of these as words appearing in sequence, and we have a one-hot encoding of each word, and we have an entire dictionary of all of the words in our corpus. Right? So we can model, for example, our a sub t is equal to b plus w times h sub t minus 1 plus u times x sub t, where a sub t and h sub t is in some little d-dimensional space. Okay? And then we would write h sub t is equal to tanh, the hyperbolic tangent of a sub t. So a sub t is just a linear function of the input and h sub t minus 1. And typically our hidden states, we're going to, we just tend to see better performance in our neural nets if we constrain its output space using something like tanh. So this is quite common, using tanh on in recurrent neural nets as our activation function. So all that's happening is this is so in words we could write h sub t is a hidden unit, and it's a function under a fully connected layer. So let's just call it, it's a fully connected layer. Layer output, where the fully connected layer has a tanh activation. So if we were to construct this neural net by hand, we would say that h sub t is a fully connected layer with tanh activation. And the input, and this is kind of the interesting part, is not just x sub t, but it's also h sub t minus 1. Oftentimes, and let's just enumerate a couple more dimensions here. So A and H are in Rd, so D is presumably smaller than P. P is extremely large, it's the number of words in our dictionary. D is our hidden state space. And so U here and W here, U is going to be D by P. W is going to be D by D. D by D. And B is going to be in RD. Right? That's just what is required to make the dimensions work out. In this case, our RNN, it can be written with the following thing. We have our hidden state, and this is a bit of a shorthand that we can write. We just draw a loop, and when we have a loop like this, we're going to assume that implies that there's this type of temporal dynamics in play. Okay, so this is a shorthand for this recurrent neural net. And this is a recurrent neural net just because there are certain units that are recurred over and over again. Right, in this h1, this is a special case where there is no h sub t minus 1. We can just think of h0 as equaling 0 in this case. So h0 equals 0 as being input for this. Okay, so this is our first recurrent neural net, and it's any neural net that takes that form, where the neural nets are repeated where these layers are repeated. Okay, and so at a given time t, we need something to train this with. So we haven't specified any loss functions. We haven't specified any supervising variable. So let's let y sub t be some response at time t. So the choice to have some response at time t and not be sort of associated with the entire document is really going to depend on the application. So an application where you might have one response for every single time t is neural machine translation, where you're trying to translate English, for example, into French, and you're trying to do it in a way that translates entire words or entire phrases which have been, you're trying to just translate the words one at a time. Now, this isn't going to be the most sophisticated or best use of way of creating a neural machine translator, just because you're not necessarily going to be translating each word one by one. But this is one way to think about it. And then you get a response variable for each input word.